nowadays these kind of questions are quite common. I just happen to flip through the A-level question, right? So for example, one of these is like that already, whereby you have this kind of amide, this kind of amide, and you are supposed to predict the products after they perform some kind of reaction. So this is just one kind of these kind of questions. It can either be amides or esters, right? So you have to know what you will become, but it's in fact the same as the typical kind of amides, right? So for example, if let's say you have ester, right? After you reduce it, make it thicker, right? After you reduce it, what will you get? You'll get two alcohols, right? One is this, the other one is like that. So now, what if you have this thing and you reduce it? It's the same, isn't it? So in order to picture this, right, first you break here, separate the two, okay, change this to a OH, change this to a OH. So for this is the same. You can do it step by step or do it all together, it doesn't really matter. So if you do it step by step, you'll cut here, this part will become an OH, this part will become the carboxylic acid, correct? You're only adding a H here. That's what we are doing to here also, right? Afterwards, remember this is the reducing conditions, so you reduce this carboxylic acid as well. So if you reduce a carboxylic acid, you'll have your alcohol, correct? So now for this question, you just have to connect the two together, and this will be your product. Or you can consider cutting these two simultaneously, it doesn't matter, right? You'll still get the answer. So this is for ester. Same thing for hydrolysis or whatsoever, you can think of this first before you think about this, right? So you can try the one for amide. Okay, there's one amide there, right? So what will you get for compound F? What is compound F? From compound C to compound F is a reduction, correct? So if let's say you have an amide and you reduce it, right? What will happen? Remember, reducing is the same as removing oxygen. This is what you have learned already. So if you reduce an amide, you just have to simply remove the double bonded O, correct? you can refer back to the mechanism. I already told you that it is actually a nucleophilic substitution reaction, right? Or you can call it reduction. So for this reaction, you don't have to know the mechanism, right? But you have to know these will convert what to what, right? Usually students get confused with amides and esters, because for amides this is what you'll get, and for esters this is what you'll get. Slightly different, right? For amide wise you only have one product, but for ester you have two products, and both are alcohols, like what I mentioned just now. This is the difference between the two. Okay. So for the first one, you just have to remove the two C double bond O, right? And this is what you get, right? Which is just this tertiary amine. And then for compound D, you see that I stated something like acidification and elimination, and you obtain this product, correct? So if you work out the double bond equivalence, you realize that everything is there, right? But this side, the only possibility is that this side is like that, right? There's no other possibilities really if you work out the double bond equivalence, right? So now your aim is to get from compound A via compound B to compound D, right? So of course the first thing that you do is to count the number of carbon. You realize that there are 2 carbons less, right, for compound D. So this hints you that you should think of a step down reaction. And remember, we have learned very few step down reactions, right? So one of the step down reactions is you have an alkene. Suddenly you have this part missing, right? This one you already know. This is one option which you think that which this one cannot undergo because there are no alkenes, right? Another step down reaction you have learned is the iodoform reaction. Okay, you have structures like this, and you react it with iodine in NaOH, and you will have your carboxylate. Okay, so you have 1 carbon less. So for this case, it fits this criteria, and since it has got 2 of these groups, you can have both of them removed, both of these 2 carbons removed, right? So after this reaction, this I2NaOH, right, you should get this product. Okay, so afterwards you perform acidification. Both of them will become carboxylic acid, right, because just now you added the base. So afterwards, elimination will give you that product. You have not learned this reaction, but I already hinted you elimination, which is the loss of water, right? So loss of water is just this H2O that is gone, and this gets joined to here, right? Even though you have not learned this reaction, they can still give you the conditions, right? I ask you to predict products, and don't worry so much because there won't be so many options for a product. There should more or less be only one option, right? So you don't have to trial and error. Okay, so that is for step 1. You are using I2NaOH. And then for compound E, same thing. If you reduce it like what I said, right, you should get this thing, 2OH, okay, which is this one. And so how do you get from compound B to compound C? You see that you are getting from carboxylic acid, something that looks like carboxylic acid, to an amide, right? You know that you cannot just throw in an amine and let it react with carboxylic acid to give you amide, because that won't happen. The only thing that will happen is an acid base between them. So in order to form an amide, right, you should have this intermediate in your head, right, which is your acid chloride. You have to convert to an acid chloride first before you get amide. right? So you have to get to this first, right? Before you add in your amine, which forms your amine. So what is the condition for this conversion? From compound B to this. How do you get from B to this? You need two steps, right? First you need to acidify because it's in the carboxylate salt form. So you have to add H2SO4, right? Dilute or not doesn't really matter, right? Because you're only using it to acidify it. Second step, how do you convert carboxylic acid to acid chloride? Yes, you can use PCl5, PCl3, etc. Right? There are tons of ways. And you'll get this. So how do you get from this to this? What do you add? What do you add? Remember, it's not a H, it's a methyl, right? So since it's a methyl, you just have to add methyl amine. Correct? Quite straightforward, right? So CH3 NH2, and that's it. Okay? Can So now, since you already practiced this question, can you try these two? It's quite lenient, 2 marks each, right? It's also quite wasted if you cannot do. Just B can already. This one is hydrolysis and not reduction. Think not. So for this, since they didn't specify whether it's acidic hydrolysis or alkaline hydrolysis, you can indicate either, right? Just make sure you draw your charges correctly. So for the first one, I assume it's acidic hydrolysis, right? So there are 2 amide bonds. What you will do is you will have to cut here, correct? So now you will have 2 groups here. Here become OH, here become OH, right? So for this nitrogen, same thing, you become NH2 plus and NH2 plus, since it's acidic conditions, right? And that's all. If it's under basic conditions, then here will be COO minus, COO minus, NH, NH. But you have to indicate whether it's acidic or alkaline hydrolysis, which is part A, right? If your part A is acidic hydrolysis, then this one you do acidic hydrolysis. right? But you'll be wrong if you draw COOH and NH. There are no charges, right? Because what are you trying to say? Is it under acidic or basic? Right? So that's all pretty much like that, right? And then for the second one, same thing, I will assume is acidic hydrolysis. For this one, it's a bit confusing, right? There are a few amide bonds, 1, 2, 3, 4, right? There are 4. So I can settle this one first. Here will become OH, here will become OH, right? Here will become NH2 plus, here will become NH2 plus, right? But there are still amide bonds here. So what I will do is I'll break here, right? And here will become NH3, NH4 plus. Here will become NH4 plus, correct? And this, common sense tells you, is carbon dioxide, correct? Because you have a carbon, you have an oxygen, what else can it become? So you have this part, this thing, and this thing, 3 products, okay? Here we are, let me think. Sorry, my bad. This shouldn't be this thing, right? If it's under basic conditions, it should be a carbonate, right? CO3 2 minus, because this is not an oxidizing condition, right? So it should be CO3 2 minus. Sorry, H2CO3, since it's acidic conditions, right? If it's basic conditions, this is acidic, right? If it's basic conditions, then you'll be CO3 2 minus, right? So take note. Okay. Yeah. So let's try another question. Question 20, right? So why is the alpha carbon more acidic? Okay, can you still remember? In fact, I already placed a section on this, right? Why is this acidic? I compared it with your carboxylic acid, correct? So I first asked your, right, why are carboxylic acids acidic? And then I went ahead to say that after you deprotonate it, these can delocalize, correct? Which stabilizes it. Because for acidity, we always look at the stability of the conjugate base. So same thing for this, right? After you lose this hydrogen, it can also be resonance stabilized, just like your carboxylic acid. That's why it's acidic, right? And this answers your part 3. Okay, you can just draw this structure and say that it is. You can say that the p orbital overlaps with the p orbital of the carbon adjacent to it, and resonance can occur, which stabilizes it. Right, just like how you explain carboxylic acid, right? But put your explanation in context. Okay. Part 4, name the type of reaction that has taken place between the ester molecules. So for this case, it's quite obvious, right? You are actually kicking out an R prime OH. Okay, this is actually a condensation reaction. Or you can call it a nucleophilic acyl substitution, right? Just for your info, you cannot see it, right? Now imagine I give you this reaction, right? This plus this. This is an esterification reaction, right? You know that esterification reactions are also condensation reactions, right? Whereby you have this plus H2O, right? So for this case, it's exactly the same, just that I'm changing this to an ester. This, I change it to a carbon nucleophile, which is at this position. Right? I'll still have something like that, right? Whatsoever here, plus an R prime OH. So compare the bottom reaction with the top reaction, you will see that they are more or less the same. Just that I'm changing this to an oxygen nucleophile to a carbon nucleophile. Right? Else is the same. If you look at the name, right, it's discovered by a German chemist. His name is called Claisen, right? This reaction is actually called Claisen condensation. They of course remove the word condensation, otherwise, right, why they won't ask this question. Okay. And just for info, if you refer back to the notes, I've already placed the Claisen condensation reaction there, right? I skipped it the last time. So next, part 5. 2 molecules of ester undergoes the above reaction to give methanol and the following organic product. So what is the structure of the ester? Actually, they don't even have to tell you it's a methanol, right? You should be able to tell that it's a methanol, because in your product, you see the ester, there's already a methanol there, okay? So for this, it's just a pattern finding kind of question, right? So if you can't see the pattern, right? If this is your product, in order to deduce the starting material, right, you just have to draw something like an imaginary line, right? Like that. So these are your 2 starting materials, right? And for this case, you can perform the same thing, and you will see that the R here is actually the CH3, right? And this is your CH3. And this is your CH2CH3, right? So in fact, the 2 starting materials, the 2 sides are symmetrical, they are the same, right? Which means your ester is this lah, right? Nothing else. And after you get a product, you can work forward and see whether you'll get a product. Right? And just to prove my point that they can test you on reactions you have not learned before, if you look at the last one, right? Adipic acid undergoes esterification to form the following. The 2 ester groups can react intramolecularly to give a cyclic product, an ethanol. And they ask you to draw the structure of the cyclic product, right? Certainly you have never learned 2 esters reacting together intramolecularly before, right? But for this case, more or less, there's only one product, right? And they already told you that it's a cyclic product, right? So what's the product? Sorry. Oh, this is in the context of the Claisen reaction, right? So you have, okay, my bad, ignore what I said just now. So you have these 2 esters, correct? This is your ethyl one. 1, 2, 3, 4. Right? So now you have to perform the Claisen reaction on this molecule. And it's an intramolecular reaction, right? They always like to play this kind of game. They give you an example in the linear form, and they give you something like a cyclic form for you to draw, right? So same thing, you just have to follow the same pattern, right? So first locate your alpha carbon. Here or here doesn't matter because it's the same. This is the alpha carbon, right? So how do you get a product? For the example that I give you, you just have to remove the OR, connect this carbon, in other words, right? If you have these 2 ester, right, you just have to remove the OR from one ester, right? And then connect this here, and you have your product. Correct. So for this, same thing. Let me draw the line. Right. This is how you get a product. So no matter what is connected here, doesn't really matter, right? Even if it's like that, same thing. I remove the OR, look for my alpha carbon, and then connect it here. Okay. So for this is the same, isn't it? I first look for the OR, which is this group. It can be anything, since they use OR, right? So first I remove this. Afterwards I look for my alpha carbon. It can't be this reacting with this, right? So it got to be the one further away. So now I just have to connect here to here and draw in a better way, right? So if you get confused easily, you just number them, right? 1, 2, 3, 4, 5. So this is a 5-membered ring, right? 1, 2, 3, 4, 5. So on 1 there is a ketone group. 2, 3, 4, 5. On 5 here there is this ester group which we didn't touch just now, right? So CH2, CH3, and I have my answer. Okay. Right, let me give you another extension, right? Just now we have seen from non-cyclic become non-cyclic, and then the question asks a non-cyclic become a cyclic, right? Now what if my starting material is cyclic? In other words, what if now my starting material is this? Right? And I tell you I undergo the same Claisen reaction. What product will I get? Okay? Can you try drawing the product? Using the same method, right? This is like pattern finding, right? You've really done such questions in primary school, I guess. And there are many ways to do it. So for primary school, you often see these kind of questions, right? And then they ask you what's the next pattern. Some people might think that might see as a shape, right? Triangle, square, pentagon, triangle, square, pentagon. The next one must be triangle, correct? This is how you see it. But some people might see that, okay, triangle, 3 sides, square, 4 sides, pentagon is 5. So again, 3, 4, 5, 3, 4, 5. So this must be 3. 3 corresponds to a triangle. They might do it in this way. So it really depends on how you see the pattern, right? Of course, there are other ways to see such patterns, right? I just find that seeing it this way is the most straightforward, right? Removing the COR and then connecting it like this, right? You might have other ways, so don't die, just use my way, right? If you think your way is easier for you, you can go ahead, right? So for this case, same thing. I have to cut this bond, right? But if I cut this bond this side, I don't just erase, it will be OH, like what the question say, right? It will just be a free alcohol. Afterwards, I find my alpha carbon, right? So my alpha carbon is here, this carbon here. I can of course take this, connect to here, or take this, connect to here, but I don't take this and connect to here, right? It's not gonna react with itself, the alpha carbon, right? It's always reacting with another ester group. So I just take this, connect to here, right? I don't have to draw a straight line, I can just draw a curve, right? Later on, then I straighten it. So okay, I confirm this is my product already, then I just count or number them 1, 2, 3, 4, 5, 6, 7, right? So I just draw a 7-member ring and just label it 1, 2, 3, 4, 5, 6, 7. So on carbon 1, I have 1, 2, right? I have this group here. So this part I settled already. Next on 7, I have a ketone, right? And then at number 3, I have oxygen there. So I just replace this carbon for oxygen. And on number 2, I have another carbonyl group, right? So I have my product already, right? Now just imagine how many ways are there to ask these kind of questions, right? Endless. If you didn't notice, for part 5, they asked the backward reaction, correct? And for part 6, they asked the forward one. Same thing for this. I can draw this product and ask you to predict what's the starting material. That will be even harder, correct? But same logic, you can just find the pattern, right? You can go back and try yourself, right? Can I get from this back to my starting material or not? Okay? So usually when I do questions, I don't do a lot of questions, but I tend to think of these kind of possibilities, right? And ask myself. So one question you can do for too many times, right? So let's try question 21. Next one. Do you realize that part 1 is the same? Right, same question, right? Why is it acidic? So again, same thing. This one no need go through. So you can just do step 2, right? Do question 2. So if you have a base and add it to alkane, of course it won't react, right? You already learned that alkanes are inert, but stating that they are inert doesn't explain the question, right? It's just stating, we are not explaining. So why the first acid base will not occur? Because whenever we talk about stability of whenever we talk about acidity, we always look at the stability of the conjugate base, right? So for this case, the conjugate base, which is your, what do you call it, ethyl minus, right, is not stable, right? That's why it can never act as an acid. because now you are forcing the alkane to act as acid, right? Another way you can say that is that the CH3O minus, which is your methoxide, is not a strong base, right? It's not strong enough to deprotonate your alkane, right? You can always refer back to the ARIO rule to check why alkanes are not acidic, right? Because none of the ARIO rules favor alkanes. And then for the next one, it seems okay what? It's an alpha hydrogen, but why you will not form the second species? If this is correct, so why wouldn't it deprotonate this to form the desired product?
Because the H is more easily lost.
Yes, okay. So now this is something known as chemoselectivity, right? You are actually selectively reacting with this H instead of this one, because this is supposedly the more acidic, or you can say the more acidic hydrogen, right? So that's why this is more likely to form instead of the other side, right? Because this is more acidic. So now the question is, if let's say di-di, right, you want the minus charge to be here, what should we do? One way that I can think of is, before I do anything, convert these to an ester, right? It can be any ester, doesn't really matter, right? Afterwards, you add your CH3O minus, so now there's no H there to hinder it, right? So now you can put a negative charge here. After some kind of reaction, after everything react finish, right? Maybe this kind do something else, right? React finish really, then you hydrolyze it. This is an ester one. After you hydrolyze it, you will go back to your carboxylic acid, right? It's quite versatile. So this is one way that you can do it, right? So now, part 3. So tell me how many products you will get first. For part 3. How many possible products are there? How many products? Nicholas, how many products?
Just one.
One?
No.
If you throw in 2 esters and a methoxide, so you only have 1 product? How many? Is it 1 or 2 or 3 or 4? Remember, it can react with itself also, another one of itself, right? So theoretically, you should get 4 products, correct? Theoretically, this alpha carbon reacting with this ester. There's 1. This alpha carbon reacting with this, there's 2. Right? These 2 are different. This reacting with itself, this reacting with itself. Right? So you have 4. So please take note, if you draw 1 less, then marks will be gone. Right? A lot of people just draw 2 without realizing the fact that you have 4. And just for information, right, this group here doesn't really affect which alpha carbon attack where, right, because this group will still be here as an OR, right. It doesn't really do anything, just that it gets kicked out and the OR is still here, right. So first, same thing, same logic as just now, right. Now remove this and connect the alpha carbon to this, right. This is one of the products. So if I draw it in a proper way, this is what I will get, right. This is 1, right. Another way is this attack here, right. So same thing, I remove this OH, attack this thing, sorry not OH, OR, and then I attach it here, right. So for this one, I'll add this, right. This is my second product. This shows that these 2 products are different, right, if you didn't realize. And of course, it reacting with itself, this one is quite straightforward. You have this, okay, and this reacting with itself, which you have this. Right. Again, you can just follow the same pattern finding kind of approach. And you have 4 products. Okay, so you can go back and try. And 21, part 4. Now they want you to draw the starting material, right? Finally, a question that's challenging enough. Okay, but not that challenging. So now you have to consider the reverse. So same thing, pattern finding, right? So you can work from the example given. So you have this group, how do you convert to this, right? First step is, of course, you have to find this thing here, right? This group. Afterwards, you see that in order to get from here to here, you just have to break this bond, right? So after you break this bond, right? After you break this bond, you have these two fragments, and then you just add the OR here. So same thing for this. First look for that shape which is here, right? Afterwards, you break this bond, not this bond, this bond. So after you break this bond, you have this, right? And then you just have to add the OCH3 here, and you have your product. You can see this pattern, you can do this question within 30 seconds, right? It's just like that, it's not that difficult, right? So now let's attempt 18, 1-8. For this question, if you apply what I've taught you, even if you tikam, you will know that A is correct, okay? Why? Because I already emphasized that your acid chlorides are always the most reactive, right? I'm really giving you the trend. If you flip back, you'll see, right? And your amides are the least reactive, as always. There's no change. So the only possibility is A. Okay, this is one way to do it. Another way to do it is by using what they say here, right? Leaving group ability, which is related to basicity. The less basic, the better is ability to leave. In other words, this is your ARIO rule once again, right? So you are now basically comparing Cl minus with this, right? You are comparing the leaving group stability, right? Which one is the most stable group? So now if you compare the three, Cl minus, O minus, and N minus, right? By ARIO rule, A atom, right? Can you still remember what atom tells you? If they are from the same period you compare, if they are from different groups, yes. If they are from the same period, you compare electronegativity. If they are related like that, you compare size, correct? So for these three, pretty obvious that Cl minus is from a different period, okay? It's larger than O and N. So Cl minus will win, right? So it's the most stable because it's the largest. Therefore, it should be placed first. For these two, you have a O minus and N minus, right? Same thing, atom can differentiate it, right? Which one is more electronegative? O, right? If O is more electronegative, you can stabilize the negative charge more. So this is more stable than this. In other words, the stability follows this trend, which means your reactivity should follow. It should be D, right?
Yeah.
The arrow is like that. Okay? So you should follow the other way around, right? Which is D. Okay? In fact, you don't even have to care about the mechanism. Sometimes they just draw it to confuse you, right? So let's try the last one, question 8. Which one? D, right? Okay, this one already emphasized a lot of times, right? Take note of which point is broken. Otherwise, this question you won't be able to do. Okay? So you can go and attempt other questions. So more or less, that's the important questions for carboxylic acid. Let's attempt the true-false questions first. structures of amines, it can be classified into primary to quaternary, right? And there are some special structures below. So for the first one, which is conjugated with an alkene, it is known as a enamine, right? Because there's an in and an amine. Well, for C double bond N, it's called a imine, and you have seen it for your 2,4-DNPH that product, right? That is known as an imine product. And you have your phenylamine as well. So for physical properties, surprisingly, different degree of substitution have different major intermolecular forces, right? Take note, I'm saying major, doesn't mean they only have that, right? For primary and secondary, the major ones are hydrogen bonds, hydrogen bonding. For tertiary, it's PD-PD and ID-ID, and for quaternary, it's ionic, right? You should rationalize why, because tertiary there's no NH, right? And for quaternary, it's charged, so it's ionic. So alcohols have higher boiling points than corresponding amines because they can form stronger hydrogen bonding due to the more polar OH, right? So if you compare the boiling points of the three species below, their M are about the same, but their intermolecular force are not that similar, right? For example, your methylamine, which is a gas at room temperature, while your methanol is a liquid. Okay, although all of them have hydrogen bonds. Solubility wise, shorter amines are soluble. For example, your primary and secondary, they are soluble, but for tertiary it's not that soluble because there's no hydrogen bonds, right? They can only act as hydrogen bond acceptors but not hydrogen bond donors because there's no NH, but they contain a lone pair, so they can bond to, say, water's OH, the hydrogen, right? So same thing as your hydrophobic tail grows longer, it gets less and less soluble, right? Therefore, your phenylamine is only sparingly soluble because it has got a large hydrophobic benzene ring, although there is a NH2, right? And on the other hand, quaternary salts are highly soluble because they can form ion-dipole interactions, right? Since they are ionic in nature. It's just like dissolving salt. So now, will amines be more soluble under acidic or basic conditions? We have done one question similar, right? For carboxylic acids, we know that carboxylic acids are more soluble in basic conditions. So for amines, they will be more soluble under acidic conditions, right? If you can remember how I explained. I wrote the equilibrium and then I told you how the equilibrium will shift if I add more base or if I add more acid. Okay, you can use the same way to explain. Next, basicity of amines, same thing. For basicity, we compare the availability of the lone pair. A more available lone pair means a stronger base. You can also compare the stability of the conjugate acid, up to you, right? So same thing, if the conjugate acid is stable, the amine will tend to get protonated and be more basic. So for aliphatic amines, they have alkyl groups which are electron donating. So this increases electron density on the nitrogen, hence making it more available to accept proton and more basic. This is the chain of thoughts, right? Whenever you explain such questions. But tertiary amines have a lower basicity than primary and secondary amines. This is due to the presence of three bulky groups, which hinders protonation. Solvation effect also plays a part, right? You have not learned this solvation effect, but it's actually very, very easy to understand, right? For example, you have a primary amine, you have ammonia, right? After you protonate it, you have NH4+, right? NH4+ can only exist in aqueous solutions. There's no way of forming NH4+ in, let's say, oil, correct? Because it's not going to stabilize it. So in water, what is actually stabilizing is actually water, right? Like what I said, ion-dipole interaction, right? Now, if let's say you add a methyl group, the same thing can occur, but the solvation effect is lesser because now there's a hydrophobic CH3 group here, which somehow hinders the stabilization. So as this group gets larger and eventually when you reach a tertiary amine, right, you have three of these groups surrounding it. Let's say you protonate it, right, this is the species that you'll form. It'll be very hard for water to approach it and to stabilize it. So that's why this doesn't really like to get protonated. Okay, this is the solvation effect. Of course, you can use the steric hindrance to explain, right? So take note. And lastly, for phenylamines and enamines, due to the overlap of the p orbitals, right, it's always the same kind of explanation, right? For your phenylamine, and for your chlorobenzene, right? Why their properties are like that, right? It's always the same. The p orbital overlaps sideways, delocalized, blah blah blah, right? It's always the same explanation. So due to the delocalization, the electron density is lowered on your nitrogen, so that's why it's the least basic. So this is the trend. Take note of where the tertiary amine lies, right? So your tertiary amine, it's more basic than ammonia, although it's still sterically hindered, right? But less basic than your primary amine and your secondary amine. So take note of the trend, okay? So you don't get it wrong. Next part, once again, we have our ARIO rules here. You can predict basicity as well, right? And basically the concept is the same. If let's say we are comparing basicity, we always look at availability of the lone pair, right? While for acidity, we look at the stability of the conjugate base, right? Always these two. So for the same period, electronegativity is the dominating factor once again. So if you look at the right hand side, you have your amine and your alcohol. So oxygen is more electronegative. It pulls the lone pair more towards itself, less available. Less available means it's less basic, right? So your amine is more basic. Another way, like what I said, you can talk about the stability of the conjugate acid, right? Depends on which one you want to talk about, but it's the same idea. Now for the same group, if they are from the same group, you have phosphorus and nitrogen. Same thing, phosphorus is larger, right? Because it's further down the group. So this is like your delocalization. If it can be delocalized, if the positive charge can be delocalized over a larger volume, you'll be more stable. So if it's more stable, you'll be more basic, right? So your phosphine species will be more basic. Okay? Can again, it's the size factor that dominates. Next is your resonance, which is your R, right? So if the above cannot differentiate, you have to use the resonance concept. First, we compare the ability to form resonance structures. So if you look at the two species, the left side, the lone pair is localized. For the right hand side is delocalized, right? If it's delocalized, the lone pair will be less available. Less available means it's less basic. Okay? While for the one on the left hand side, it can be delocalized and already drawn the resonance structure there, right? Sorry, for the left hand side, it cannot be delocalized, right? Only for the right. Now, if both can be delocalized, then you have to look at the extent of delocalization. For example, phenylamine and your enamine. So for your phenylamine, the lone pair is delocalized over a larger area compared to your enamine. So therefore, your phenylamine is less basic. Okay? Exactly the same concept as your acidity, right? Next, inductive effect. For these two species here, it's quite obvious that the one on the right hand side, it's less basic, right? Because there are three Cl groups, which pulls the electron density away compared to the left hand side. Okay, so vice versa, if they are electron donating groups, then you intensify you will increase the electron density, right? Vice versa. Same thing, distance effect also plays a part, how far the electron donating or withdrawing groups are. And next is your orbital effect. So if you compare these two nitrogens, right? For the one on the left, the nitrogen is what hybridized? What's the hybridization state of the left hand side? sp2, right? For the right hand side is sp. Same thing if you were to look at the shape of your sp2, sp and sp3, you will see that for sp2, it is less round or less close to a nucleus than your sp, right? So for your right hand side, that nitrogen, the lone pair is closer to a nucleus, so it's less available. If it's less available, that means it's less basic, right? Again, same idea. Same thing, the ranking of the ARIO rule is just like its name, ARIO, right? Always consider the first one before you consider the second, right? Only if you cannot differentiate, then you consider the second. Okay, now we try this example. So which one is the most basic? First one? Do you agree it's the first one? If you apply the ARIO rule, A doesn't really help us that much. So we look at R, right? Resonance. For these two, the first one, of course, there's no resonance structures, right? For these two, especially the center one is the problematic one, right? Nowadays, a lot of questions like to ask about this one. This is known as pyridine, by the way, right? It's quite harmful to male, right? Don't know why, not harmful to female. So this is pyridine, and this is your phenylamine, right? So now a lot of students have the misconception that for this one, somehow the lone pair, if you were to draw the lone pair, right, it can be delocalized. Do you think it can be delocalized? Do you think it can be delocalized? This one definitely can, right? You already learned it. Can these delocalize? Now, what is the hybridization state of this nitrogen? Sp2, right? This one you should know how, right? Sp2, So now if you were to draw, and you should know that this lone pair is in an sp2 orbital, correct? So if you were to draw this in a side view, right? This is what you'll get. You'll get all the unhybridized p orbitals of carbon, the unhybridized p orbital of this nitrogen, right? As well as this, and this sp2 orbital, right? For this sp2 orbital, this electron is bonding with this carbon's sp2 orbital, right? To form this sigma bond. Same thing for this, and your lone pair lies here. Do you think the lone pair can overlap sideways and be delocalized with the ring of unhybridized p orbitals? No, you can't, right? This is clearly 90 degrees to this unhybridized p orbitals. There's no way for you to delocalize. Okay, so for pyridine, this is localized. In other words, it's not delocalized. But for this, it is delocalized because for this case, right? For this case, you have your carbon here. Afterwards, you have the nitrogen here, right? For this lone pair, right? It is like that. This is sp3, correct? This nitrogen. So sp3 is like that. Although it's not strictly speaking 90 degrees, but it is still at an angle sufficient for sideway to overlap. Okay, so this one, it is delocalized, this is not. Alright, so for resonance wise, now you know that only this is delocalized, right? So since only this is delocalized, this will be the least basic, right? So what about this? We cannot use R anymore, alright? because if you compare these two, both are nitrogen, both cannot delocalize. What about inductive effect? Not really, because everything else is carbon, right? So we have to look at the last factor, which is orbital. For the first one, the nitrogen lies in an sp3 orbital. For this, it lies in an sp2 orbital, right? We just now mentioned that your sp3 nitrogen is more basic because the lone pair has less s character, right? So you can think of it like that. This is your sp3 and this is your sp2, right? It's more fat, right? Your sp2. So if this is a nucleus, this is further away. If this is a nucleus, it's closer to it. So this is less available, right? So therefore your basicity should be like that, right? And your the first compound, right? If you flip to your prelim questions, you can see this one, right? Yeah, put it. Let me see. There's one something like that here. Yeah. I think there's an MCQ question which is like that. Anyways, maybe I forgot to put. Right. So just take note. Right. Remember it's your NYJC question. 2011 question. Right. So next, isomerism of amines. Right. Let's look at isomerism once again. Nitrogen atoms, particularly in imines, can exhibit geometric isomerism if the two groups bonded to each other of the double bond are different. Right? So you can have your Cs and your trans. C the R group. So for example, if let's say I have an aldehyde, right? This aldehyde, and I tell you I ran it with 2,4-DNPH, theoretically I should have two products, right? Because for a 2,4-DNPH, for one of it can be like that, the other one it can be like that. These two products, right? These two are isomers. But we always just draw one because it doesn't really matter which one. You will still give me that color change. Okay? So I can have cis trans isomerism. Take note for imines only, right? CN double bond. Next, optical isomerism. Quaternary ammonium salts, which have 4 different groups attached to a nitrogen, can exhibit optical isomerism. Right? This is just like nitrogen with 4 different groups. Just that now my nitrogen have a positive charge. Right? But generally we do not consider tertiary or secondary amines to exist as optical isomers. If you check out the structure on the right, if let's say the 3 R groups are different, R1, R2, R3, theoretically speaking, you will expect to see optical isomerism, right? Because the lone pair itself can act as a group. Correct? But the thing for amines is that we don't really consider them as to exist as optical isomers because there's something special about them, which is their their inversion, right? We call it a nitrogen inversion. So what actually happens is that just pretend that this is an amine, right? What happens is originally the lone pair is here. What happens is you just flip to the other side, right? And there you have it, the other isomer. So this flipping is actually very, very fast. In other words, you can't differentiate the two optical isomers. So that's why you don't consider it to exist as optical isomers, right? Since it equilibrates very fast, right? This is just the analogy of this image. So next, reactivity. But take note, quaternary amines can have optical isomers. It's only the others, right? So for amines, reactivity. Amines contain lone pairs, so they can act as nucleophiles. And they are more nucleophilic than alcohols, right? Because they are less electronegative, right? Amines can take part in many reactions such as nucleophilic substitutions, nucleophilic acyl substitution reactions, and nucleophilic addition reactions, etc. Right? You have seen these examples, so can you write down these examples? right? Just give me the general equation can already, right? What react with what? This one somehow is similar to this question, A-level question, right? The ammonia molecule can react in various ways, as an acid, as a base, as a nucleophile, as an oxidizing agent, as a reducing agent. So they want you to describe, right, ammonia acting as what for all these reactions. Right, so it's important to identify what's happening, right? So you can try this first. The teacher got asked you all to buy TYS, right? Is it? Right, so you should have all of these. So for nucleophilic subs, it's quite easy, right? It's just NH3 reacting with your RX. Nucleophilic acyl substitution, this one already seen, right? Ammonia reacting with your acid chloride, okay, to give you your amides. This is your nucleophilic acyl substitution, right? So for next part, preparation of amines. You can prepare amines by the reduction of nitriles, right? So if you reduce your nitrile, remember the trick is just to add H2 between C and N and add H2 at the end, right? There's reduction. You can use lithium aluminum hydride or H2 nickel, but not NaBH4. Reduction of amide, you can only use lithium aluminum hydride. The trick is just to remove the C double bond O, right? This one already told you just now. And next one, nucleophilic substitution. You will have your ammonia being introduced, and you have your amine being generated, right? Remember to use SS concentrated, otherwise you will have a high chance of getting a quaternary ammonium salt, right? And that's why we always tend to avoid this method. And I already told you how to bypass this problem, correct? By using acid chloride followed by reduction, right? The other lesson. So let's try step 4, synthesis. You can just write 1, use 1, 2, use 1, right? first one you should get it right. Is your NaCN, right? In ethanolic solvent, right? Afterwards, you have this. Afterwards, you just perform reduction, right? H2PT or lithium ion hydride, doesn't really matter. This is for the first one. For the right hand side one, you just have to throw in excess con NH3 in ethanol, right? Quite straightforward. And then for the bottom one, you have to perform a 3-step reaction, right? The first step is to convert it to acyl chloride, okay? And then you make it into a amide. Yes, and then you reduce, right? You've already done this quite a few times, right? So please fill in the reaction conditions, right? Next. 2 more. We have done something similar before, okay? How do we control which one to add to, right? Well, the first one is quite straightforward. In order to add that methyl group to methylamine, you just have to throw in CH3 iodine or CH3 bromine, right? And what is the condition? Limited, right? Take note. If you use excess con amine to prevent multiple substitution, then the reverse is the limited distinct. Okay? To prevent multiple substitution. This is the first one, the one on top. What about the one below? You can't just throw in this. You always add to amine. So you must somehow make it more nucleophilic than amine, right? For this case, remember just now I said that amines are more nucleophilic than alcohol, right? So that's why the first reaction can occur and the second reaction will not occur. But how do you make alcohols more nucleophilic than amines? Is to deprotonate them, right? So you can just add a base. So what base do you add? The answer is sodium. You already learned it, right? Only sodium is able to deprotonate your alcohols. So you first add sodium. After you add sodium, you have this species, right? Here become O minus and Na plus. If you compare an O minus and an N, O minus is more nucleophilic, right? Then you can throw in your CH3I and you will add to the O here. Okay? So this is the trick to do. Right, hydrolysis of amides. You can either hydrolyze it under acidic or basic conditions, but take note that only for basic conditions you will have a pungent NH3 gas, right? Because for acidic conditions you will have ammonium ion that's being formed, not ammonia gas. Okay, so for the first one, take note. First one you will have your carboxylic acid plus ammonium ion. For basic conditions, it will be your carboxylate and your ammonia gas. Right? And for amine recovery, this one you already learned in O levels, right? If you want to recover your ammonium, you just have to throw in your NaOH. Okay, you should be able to balance the equation. Right? This is how you can get your amine from your ammonium. Okay, it's just NH2. Please learn how to balance this equation, right? You have learned in O levels. And next one, reaction of your amines. If you react amines with any acid, they will get protonated, right? And the important thing is that you will get a white crystalline solid upon evaporation, which is your salt. Okay, this is something like your crystallization. For nucleophilic substitution wise, right? Sorry, this is not excess con NH3. It should be your limited, right? Limited Rx. in ethanol lah. Right? So this is similar to just now the negatively sum reaction, right? And you will have your NHR basically, right? If you use limited Rx in ethanol. Amide formation wise, same thing. If you react with your RCOCl, you have your amide. Okay? This one we will not draw the mechanism because we already drawn it during the last topic, right? So same thing, excess ammonia is required because the additional base is required to neutralize the acid product. Take note, after this reaction you will generate the Cl, correct? The Cl go where? The Cl is actually your HCl, right? So you actually need another amine to neutralize that HCl. So that's why for this you will need 2 equivalents of your amine, right? So example 5. So which groups will you rank with? Does it react with the left side? Nitrogen in the ring? Doesn't, right? What about the second one? Second nitrogen. Does it react? Second nitrogen from the left. Does it? Does it react?
Yeah, it does.
It does. Then what about the oxygen beside it? CH3CuCl, remember it can react with your alcohols to form what?
Oxalic acid.
Yeah, to form esters, right? So you have your CuCl, RCuCl reacting with your ROH to form esters, right? And they can react with amines to form amides. Correct, huh? So does that mean you can just find out all the nitrogen you will react with all the nitrogen, this one will react with all the OH? The answer is no, right? So these will react with these to form an amide. These will react with it to form an ester, right? What about this nitrogen? The one on the extreme right. Does it react with acid chloride? Does it? If it does, what will the product be? If it does, your product will be something like that. Correct? Do you think this is feasible? No. Okay. For all your amides, they are neutral, correct? And you have learned that amides are stable. Amide bonds are stable because you have lone pair here, which can delocalize into this C double bond O, right? Now for this case, there's no longer lone pair available here to delocalize. In other words, this is destabilized compared to the previous one, for example like this, right? At least if let's say you have a tertiary amide, there is still a lone pair here which can delocalize to stabilize it. But once you use a tertiary amine to react with this, you will form something like a quaternary amide which is not stable. So therefore you will not react with this nitrogen, right? This nitrogen, yes, this is not quaternary, right? What about this? Does it react with this? Acid chloride? Theoretically speaking, it should react, but the rate is quite slow, so we don't consider reacting. Remember, we always say that we add a base to remove this hydrogen before we react with acid chloride. Okay, since for this case we never mentioned about the base, so we will assume that it doesn't react here. Right? Why doesn't it react? Because in order for it to react, the lone pair must act as a nucleophile, right? Same for all of this, but for this case, it's delocalized into this ring. Right, so that's why it's less available. And then you might argue, for this nitrogen, there's also a lone pair, correct? Isn't it delocalized into a ring as well? What do you think? How come this nitrogen reacts, but not this oxygen, although both of them delocalize into a ring? Remember your AR rule, right? You can also use that to explain nucleophilicity. We talk about the availability of the lone pair, right? Which is the same concept as your basicity. So you can use AR rule to explain as well. Between O and N, right? Which one is more electronegative? It will be O, of course, right? So we can say that although both can delocalize, O is more electronegative, right? So it can delocalize, it is more electronegative. But for this, it can only delocalize, right? But it's not as electronegative as this. So that's why this overall is more nucleophilic than this, right? So that's why this can still react with your acid chloride. Okay, this is the reason why. Okay, let me finish this section 10, right? So reactivity of phenylamine at the nitrogen. Recall that amines can act as nucleophiles, right? Since there's a lone pair. The same goes for phenylamines, but compared to amines, phenylamines have lower nucleophilicity and basicity. Okay, because they can delocalize, but they are still more electronegative than they are still more nucleophilic than phenols, right? Because already explained here, although they can delocalize. So the lower reactivity is due to this effect, electronic effect, right? So the p orbital of the nitrogen atom overlaps with the pi electron cloud of the benzene ring. Lone pair of electrons is delocalized, resulting in lower electron density of nitrogen. Hence, nitrogen is less nucleophilic and less basic, right? So now, even though phenylamine is less nucleophilic at the nitrogen compared to amines, it is still quite nucleophilic and will undergo similar reactions as typical amines. In other words, this phenylamine compared to typical amines, there is not really much of a difference in reactions, right? They will still undergo the same reactions as this because they are already so reactive. You are only using the resonance effect to decrease its reactivity by a little bit. It doesn't really affect. Maybe you only affect the rate, that's all, right? unlike phenos, right? So for example, for phenos, I already compare the two. For the left hand side is the alcohols, for the right hand side is the amines. You can see that for the left hand side, I have to modify the reaction conditions for the second one to make it react because it's less reactive, right? But for the right hand side, although it's less reactive, I can use the same set of reagents and it can still react. This shows how reactive your amine compounds are, right? And this also explains this question once again, right? So for this question, same thing, I can modify the question by saying that I add in one equivalent of CH3 COCl, right? So this CH3 COCl will react with which one? The answer is this one, correct? Because comparing oxygen and nitrogen, of course nitrogen wins over, so I only circle these three initially. So now I compare these three. This doesn't react, I already mentioned. So it's between these two. Between these two, this one can delocalize, this one doesn't delocalize, right? So the final answer will be this, right? It's again selectivity issue. Okay, so we'll stop here for today.